So this is sort of the simplest kind of quantum Hall effect. Okay? And many Nobel Prizes have been given for this. And now we come to quantum Hall ferromagnetism. So the quantum Hall effect, as I said, the quantum Hall system is in a topological state. It does not need any symmetry breaking to happen, okay, in order to be in a topological state. However, sometimes it occurs that the system itself has some internal degrees of freedom, such as spin or valley or something else, and those things have some degeneracies and they can actually spontaneously be broken. So there can be symmetry breaking in a quantum Hall effect. And how does that happen? So let's think about the simplest case. You have electrons filling one Landau level, which is the lowest Landau level. And then in this Landau level, you have exactly the same number of electrons as there are orbitals in this Landau level. Now technically, you can fill an up electron and a down electron into the same orbital by the Pauli exclusion principle. But what happens is that when you fill one electron per orbital, then the Coulomb interaction gets minimized when they're all pointing exactly the same way. Why is that? Coulomb interaction has nothing to do with spin, but when all the spins are pointing the same way, to make the total wave function antisymmetric, the fact that all the spins are in a symmetric state means that the spatial part of the wave function has to be antisymmetric, and that means that the Coulomb interaction is less when the particles approach each other, and that is what makes the system want to be ferromagnetic. And this is the same as Hund's rule when you apply it to some partially filled shell in an atom, except this is happening at the macroscopic scale. So this is quantum Hall ferromagnetism. So even if you did not have a Zeeman coupling, you would actually have a fully polarized ferromagnet for nu equals 1. And this general phenomenon is called quantum Hall ferromagnetism. Okay, and this is spontaneous. So even if you didn't have it, even if you didn't have the Zeeman, then you would still have a certain direction in which the entire magnet was pointing. And this was pointed out in 1993 by Sondhi et al. All right, so now we have understood some of the things in the title. And now let's go on to optical cavities. So normally when one thinks of a cavity, you think of something that's enclosed, right? So you think of a box and light is bouncing around inside this box and so on, and that is certainly one type of cavity. But it doesn't have to be that way. Okay, you can have basically what are called split ring resonators. So basically a 2D sheet of metal with some holes cut into it. And then that thing has an inductance and it has a capacitance and it acts like an LC circuit. So it has some resonant frequency. And so what happens is that there are certain modes that are confined into near the region of that metal. So that can be a different type of cavity. Not enclosed on all sides, but simply a sheet of metal with some cutouts in it. Okay, so it's some kind of setup that tries to confine light in a certain region of space. Okay, and the modes that are thus confined in that region will become quantized. Just like any particle that is sitting inside a box will get quantized, light that is sitting inside some confined region of space will also get quantized. And what this thing allows is that now you can start putting some stuff into the cavity and asking how the cavity affects it. And people initially started with very simple things. Of course, they had the old-fashioned type of cavity, which is like a box, basically two mirrors, and light is bouncing around between them to create lasers. And then they started doing some more interesting things, like putting in atoms inside the cavity and asking, how does the transition frequency change as you couple the atom to the cavity and so on. This type of thing is called cavity QED. And now we have systems. You've probably all heard of cold atom systems, optical lattices, and people in the cold atom business are trying to simulate things like the Hubbard model, superfluidity, and so on and so forth. So we've come a long way since the old cavities. And now, in the last few years, last 4 or 5 years, there's this new subfield of condensed matter physics. I don't know if you want to call it condensed matter physics or AMO physics, or some hybrid of the two, which is called cavity materials. And the idea of this subfield is that the properties of these materials will undergo some profound changes when you put them inside a cavity. And the nice thing about the cavity, so whenever we have a material, like Arindam said in the previous talk, we are always looking for ways to tune its properties by doing something or the other, some tuning knob. And the cavity offers a completely different way to tune this material. Okay, you can tune the frequency of the quantized mode of E&M that is sitting inside the cavity. You can tune the shape of the electric field that is sitting inside the cavity. You can tune the coupling of the cavity and the electrons. There are many, many such tuning knobs. Okay, so you can hope that by tuning all of these, you can try to alter the properties of the material itself. And indeed, that is true. So there are many such phenomena that have been noticed in the past several years. There is photo-induced superconductivity, there's photo-induced ferroelectricity, there's the effects of the cavity and resistance. There are many, many such phenomena. And there are basically two classes of these phenomena. And one of them basically involves driving the cavity. So you have a cavity and you pump it with some kind of light, and that light then interacts with the material, and that changes the properties of the material. So that is, for example, the class to which photo-induced superconductivity belongs. And systems like that, when you're pumping the system, you will always have some kind of dissipation. The system will heat up, and you hope that you can make whatever measurement you want to make before the system heats up too much. Okay? There's a different class of systems in which the cavity is not driven at all. So you don't pump it, you just leave it the way it is, and just the fact that the quantum Hall system, or whatever it is, whatever material you have, it is sitting inside a cavity with some quantized electromagnetic modes, that itself will introduce some changes into the properties of the material. And this is happening completely at equilibrium. Okay, there is no pumping, there's no dissipation, nothing else is going on. Okay? So that is the kind of system that I will be talking about. Okay, so now let's look at some recent experiments. So here's an example of this split ring resonator that I was talking about. So this is a sheet of gold. These are experiments that were done at the ETH in the group of Jerome Feist. And he's been a pioneer in this area of putting quantum Hall systems into cavities, and he's done a number of beautiful experiments over the past several years. And so this is a sheet of gold, and there are these holes that are cut out of the sheet of gold. So the holes are cut out in some pattern that gives them an inductance and a capacitance, and there is a quantized electromagnetic mode that is sitting inside here. So you can see the color map is telling you the strength of the electric field. So there is a mode that is mainly confined to this empty region. So the rest of this is gold, this is a hole. So the electric field lives in this hole. You can see it becomes very intense near the edges, and then it's much weaker towards the center. Okay, so that is the shape of this electric field, the strength of this electric field. Okay, that is associated to this mode that, remember, this mode is not being excited. Okay, it's there, but it's not being excited by anything. You're not pumping it. Okay, and then in this, the rest of this thing, he's showing you what the quantum Hall sample looks like. So imagine this sheet of metal, and it's very, very close to the quantum Hall sample. Okay, so the electric fields of this sheet of metal, or the cavity mode, the vacuum mode of the sheet of metal, are interacting with the quantum Hall system. And so, of course, there are some contacts. You drive some current through something. You measure some voltages, and so on and so forth. So that's just a usual gallium arsenide quantum Hall system. Okay. So this graph to the right, so this is the system itself. And this graph to the right shows you what the RXX and RXY look like. Okay, so the RXX is this black curve and this blue curve, right, that are hugging the bottom somehow. And then the RXY, which should be quantized, are these step-like things. So the black line, both the black lines, the RXX and the RXY, are when the cavity has been switched off and the cavity is taken far away from the quantum Hall system. And then the blue lines are when the cavity is brought close together. So the point is that this cavity can be removed from the 2-deg, or it can be brought close to the 2-deg. So this is an in situ way of trying to tune the coupling between the cavity and the 2-deg. So when the cavity and the 2-deg are not coupled, you can see all these steps at every integer, right? Okay. Now, once the cavity has been coupled, then you look at the blue lines. And you can see it much easier in RXX. So RXX should actually vanish when the system is in a quantum Hall state. And the black line, you see that the black lines always vanish when you're close to some integer, right? But then the blue lines, you can see that the blue lines don't vanish nearly as strongly when you're near an odd integer. And so the bottom line of this experiment is that if your filling is an odd integer, say 1, 3, 5, and so on, then the quantization of the Hall effect becomes weak. Okay? And it can be even destroyed as you make the coupling of the cavity stronger. But if you're sitting at an even integer filling, there's no difference between having the cavity or not having the cavity. Okay? So the cavity is making some very serious effect on the system. Okay, so this is the integer case. Then a few years later, the same group also carried out an experiment. Here you can see a different cross-section of the system. Like I said, this was the gold sheet, which was actually the cavity, right? And this is the electric field of that gold sheet. And here they can show you how they're bringing it close together or taking it further away from the two-dimensional electron gas. And that is how they change the coupling. So now you can see that this black line is when this cavity is very far away from the 2-deg. So it has very little influence on the 2-deg. And this blue line, this light blue line, is when it's very, very close. So that's the strongest possible coupling. And let's look at this. You can see that this quantization of Rxx. So Rxx should actually vanish, right, when the system is in the quantum Hall state. It does vanish even when there's no cavity. But as you bring the cavity closer, it actually, the quantization becomes better. Okay, so notice the contrast. So even integer, there's no change in quantization. Odd integer, the quantum Hall effect becomes weaker. If you have a fraction with denominator 3, of course they haven't done it for all possible fractions. But if you have it for a fraction with denominator 3, the quantum Hall effect becomes stronger in the presence of a cavity. Okay? So these are 3 completely different effects. So obviously there's some very interesting things going on, and this was the motivation for us to start looking at this kind of system. There is some theory which was actually done before the experiment on the fractional, but the theory should be incomplete because it doesn't actually predict the fact that the quantum Hall effect becomes stronger when you introduce the cavity. Okay? So there's still a lot of gaps in our understanding of what is going on here. Okay, so let's look at how we model this Hamiltonian. So obviously, there's your momentum, right? Here's the vector potential of the static magnetic field. That has to be there because you're in a quantum Hall regime. You have to have a very strong perpendicular magnetic field. And this is the vector potential of the cavity mode. Okay, so I put a subscript C over here. And this is a fully quantum mechanical object that you can see over here. Okay, so this gamma is some constant that has to do with the normalization of this quantized electromagnetic mode. And then this is the profile of the electric field. This is the shape of the electric field that is produced by the cavity. And then these are the creation and destruction operators for the photon that belongs to this particular mode. Okay? So that is what is going on here. So the electrons are coupled, of course, to the static magnetic field, also to the cavity. The cavity has its own energy, right? It's a photon, so it's simply an oscillator mode. And then this is the electron-electron interaction, which I'm never going to write down fully explicitly. Okay, so that is the entire Hamiltonian. And now you do whatever you want to do with this. Okay? So what we are going to do is we're going to assume that this thing, this u of x, this profile, depends only on x. Now it is known that if this u of x were a constant, suppose you had a constant electric field for the cavity mode, then all it would do, it would couple to the center of mass motion of the electrons. And there would be some kind of hybridization between the cavity mode and the cone mode, which is the center of mass motion of all the electrons. And that's all that would happen. It would not affect the ground state at all. So in order to have any influence at all on the electronic system, you need to have this u of x varying in space. It cannot be completely uniform. And so what we assume is the sort of the one step beyond the fully uniform thing. We assume that it's varying linearly with x. Okay, so this is our assumption. It's a toy model. I'll say something later on about it towards the end. Okay, so now what we really want to do is we want to take the lowest Landau level limit. This is hard because at the same time we also want to keep the magnetic length, which is h bar over EB square root. We want to keep that constant, but we want to make the Landau level spacing very big. So the way to do it is to send the mass of the electron to 0. Okay, this is a purely theoretical trick. It's a way to take the lowest Landau level limit without actually letting the magnetic length go to 0. So if you just wanted to send the magnetic field to infinity, that would of course send the cyclotron energy to infinity, but it would also send the magnetic length to 0, which is what we don't want to do. So what we want to do is we want to take the mass of the electron to 0. The problem is that you will see, what happened, right? You will see that 1 over the mass of the electron appears in the coupling between the cavity and the electrons. So you can't naively send the mass of the electron to 0. So you've got to do something a little bit better. And what you do is you make a unitary transformation to something called dipole gauge. And this is the unitary transformation. And when you do that, then the coupling between the electrons and the cavity goes away from the kinetic term and it becomes something else. And then you can actually take the limit as the mass of the electron goes to 0. And here it is. Here's that Hamiltonian. So you've gotten rid of the cavity from the kinetic term and you put it somewhere else, which is over here. Okay? And so now you can then take the limit as the mass goes to 0. That will be the lowest Landau level. Okay? Yeah?
You have 5 minutes for your talk.
I have 5 minutes left?
For your talk, yes.
Okay. Yeah, I'm going to speed up. Okay. So one important thing is there is no thermodynamic limit here because the electric field is actually varying linearly in x. So you have to have systems which are finite. So let me forget about all this and let me give you just a sketch of what we did. So we did 3 different types of calculations. So in the weak coupling system, weak coupling situation, right, and the coupling between the cavity and the electrons is weak, the system is still a quantum Hall ferromagnet, and we found its spin wave excitations, and we asked when does that become unstable. Next, we carried out a DMRG, and this was Cheren's work. And again, this is completely unbiased, and what it shows you is that a strong coupling, the system acquires what we call a wedding cake structure. Then inspired by this DMRG, we also did a mean field, and we found this wedding cake structure. What is the wedding cake? Quantum Hall ferromagnet is just 1 electron per orbital everywhere. Wedding cake means you take some electrons from the outer edge, flip their spin, and put them in the center. So we call it wedding cake because the density increases in the center. And so let me show you a picture of the instability of the spin waves as you increase the coupling. This is the coupling. So you can see that at weak coupling, spin waves are fully gapped, except of course at 0, as they should be. They have a quadratic dispersion. But as you increase the coupling, they will eventually touch 0 at some non-zero value of q. Okay, and that is the instability towards the wedding cake. Here's the DMRG. Again, this is the blue is the weak coupling, and this brown, light and dark brown, are the stronger coupling. You can see the wedding cake here, right? Higher density in the center and lower density towards the edge. And finally, let me show you the mean field. This tells you the size of the region with double occupation as a function of the coupling. So I'm basically done. So let me put up my conclusions. So the point is that just having the system in a cavity with a single mode is actually enough to produce some instability in the quantum Hall ferromagnet. Okay, this was very shocking to me at first, because how can one single mode actually make an instability of an entire very large system? Of course, this system is not thermodynamically large. Remember what I said, everything varies linearly with x, so there is no thermodynamic limit. Regardless, the strong coupling phase, we know what it is. Despite the very strong coupling between the cavity and the electrons, there is no entanglement between the 2 parts of the system, between the electrons and the photons. They have an influence on each other, but they don't have any entanglement. The wave function is always a product wave function. And then, there's some obvious open questions. I'm sure you can think of many, many here. And let me end by thanking my collaborators again, and the organizers and the audience. Thank you.
there a mic or is there any?
Yeah, there is a. I have a short question. Same time.
Yeah.
So, in the context of quantum ferromagnet, when you add a hole, was shown by friends that there is a fermion structure.
Yeah.
So that means there should be a fermions in your boundary that you were talking about.
Yes.
Lattice and so on.
Yes.
We will look at it.
Yes, absolutely. So actually the thing is that we have a very toy kind of system where what we do is we have some guiding centers and then we say that everything else is just forbidden. They have some very large energy. So if you make the edge smooth, then actually you will have the spin texture at the edges. You're absolutely right. Yeah.
The second question.
Nice.
Yeah.
So, how do I physically understand why the integer state is, the odd state is getting perturbed?
Right. So because this is a spin effect. Okay, so the thing is that's why we focused on the quantum Hall ferromagnet, because the quantum Hall ferromagnet spontaneously breaks that SU2 symmetry, right? So it is that, so you're trying to pile up something from the edge onto the center, right? Whereas if you had double occupation, you couldn't do that, right? You'd have to go to the next Landau level.
So, you're saying I'm changing the filling factor in the center?
You're changing the filling factor in the center without changing the Landau level. That's why the odd. Look, the thing is that I shouldn't claim too much because this is inspired by the experiment, but the conditions are very different from the experiment.
So I have more questions. Sorry.
Okay, very nice talk. So I am continuing the same question. So when we are even filling, basically this gap is Landau gap.
Yes.
And when we are looking at odd,
Yeah.
this is basically spin gap.
Yeah.
And that gap already we know is much smaller than
Yeah.
the Landau. So this will have some impact.
Yeah.
in
Yeah.
What do you think?
Oh, absolutely. I mean, that is why they found, I think, in the experiment that the odd integers were weakened. So this is sort of the idea that we went, it's exactly this kind of intuition that we went in with in order to do this calculation, but you still have to do it to see what the effect is.
Okay, thank you.
Okay, thanks. Very nice question. So, does it matter whether the cavity vacuum is like an empty, like you have 0 photons to begin with, or if you start with some finite number of photons?
So that's an interesting question. So the point is that if you don't have any coupling between the cavity and the electronic system, then the number of photons is conserved, as long as there's no, if the Q factor is infinity and so on. Now, of course, you have a coupling between the two. So the thing is that the actual ground state of the system is a product state with a coherent state of the photon in the cavity and the Hartree-Fock state of these electrons. Okay, so there's some average number of photons, but it's not a conserved number anymore. Okay, because the Hamiltonian doesn't commute with A dagger A. So it's
Initial state can also be where you have some, let's say, n0 number of photons to begin with. And
absolutely, you can. So there are these so-called photon copies that you have in the spectrum. So you can actually take the electronic system and add a photon. That'll be another state. Yes.
A quick question about this experimental setup.
Yeah.
So the experimental setup. So you have this cavity. So is it like the in situ setup? When you are bringing the cavity close to the Hall bar.
Yeah.
Is it completely encapsulating the Hall bar, or is it like sitting on the bulk of the Hall bar?
Well, so the Hall bar is here. There's one layer which is the Hall bar. There's another layer which is the cavity. So the cavity is basically a layer of gold, a thin film of gold with some holes cut into it. So you bring the two of them close to each other, but you never make them touch. Okay, so the cavity it's a funny thing. I mean, the fields, of course, extend in 3 dimensions. So, but the metal of the cavity is really 2-dimensional, and it never encapsulates the quantum Hall system.
So I mean, is there a strong coupling between the edge modes of the quantum Hall and the cavity, or it is mostly the bulk will bring everything?
That's another thing. It's not completely clear, because the thing is that when you bring the quantum Hall system very close, then the fields are very strong throughout, both in the bulk and in the edge. But when it's slightly far away, then it's only close to the edge. Yeah.
Any other quick question? तुम्हारा तो बहुत लंबा होता है. Very quick.
So, Dipali, from this you just expect the same thing to also happen at 1/3 then?
We don't know what happens at 1/3. We know from the experiment that something completely opposite happens. Yes, so I don't know what to say.